Hello student, welcome to the one more session of analog and digital electronics. In this session, we will start the first module. So this is the syllabus of first module according to VTU. So in the first module, we will start from operational amplifier. Operational amplifier application circuits such as multivibrator, then multivibrator using IC355, peak detector, Smith trigger, active filters, non-linear amplifier, relaxation oscillator, current to voltage and voltage to current converter. So first we will see operational amplifier basics. So operational amplifier is a direct coupled high gain, high bandwidth differential amplifier with a very high value of input impedance and a low value of output impedance. So here you can see the internal structure of operational amplifier. So the operational amplifier is represented by this symbol where this one is called as inverting terminal, and this one is called as inverting terminal, and this one is called as non-inverting terminal with bias voltage plus V and minus V. So operational amplifier is a high gain, high bandwidth differential amplifier. The symbol of the operational amplifier is shown here. So this is the inverting input, and this is the non-inverting input, and this is the output. So this amplifier is connected by the biasing voltage plus VCC and minus VE. Now why it is called as an operational amplifier? The name operational amplifier because it can be used for wide variety of applications, such as operational amplifier can perform mathematical operations such as addition, subtraction, integration. Then it can be used and differentiation, and other than that it can be used in the signal conditioning such as active filters, etc. So thus the term operational amplifier is used, and in short we call this as a op amp. In short we'll call this as a op amp. So now this is the electrical equivalent model of the practical operational amplifier. This is the electrical equivalent model of the practical operational amplifier. This has got two terminals. One is called the inverting terminal where we apply the source voltage. Other one is the non-inverting terminal. So VD is the difference voltage. As I said earlier, the main purpose of the operational amplifier is to amplify the difference signal. So it is a high gain, high bandwidth differential amplifier. So VD is the difference signal of VI1 and VI2. Other than that, RI is called as a input impedance. So RI is the input impedance, and this is the gain block. And AOL is called as open loop gain. So AOL is called as open loop gain. Suppose VD is the input voltage what you are giving to the amplifier, and AOL is called as open loop gain. Then V out is nothing but AOL into VD. Otherwise AOL is nothing but V out divided by VD. This is called as open loop gain. When I represent open loop gain, that means open loop gain is the one where in which case we are not connecting output as a feedback to the input. So that is called as open loop gain. When we don't connect anything from output to the input, it is called as a open loop gain. So here this is the amplification block with open loop gain is AOL, and R0 is called as a output impedance. R0 is called as a output impedance. R0 is called as a output impedance. For ideal operational amplifier, the input impedance is input impedance or input resistance is infinite. That is input impedance infinite. So that means it is an open circuit here. That is there is no current flowing between VI1 and VI2. It is an open circuit, and output resistance is 0. output is represented by something like a short circuit. This is the theoretical equivalent of ideal operational amplifier, theoretical equivalent model of ideal operational amplifier. So when you compare theoretical model with the practical model, in the practical model input impedance is not infinity. There is a certain value of input impedance. It is not infinity, but and the output impedance is not 0. Output impedance is not 0. There is a value, but in this case theoretical value, in the theoretical model of the operational amplifier, input impedance is infinite or infinity and output impedance is 0 as shown in the diagram. So now we'll move to the one more section, that is the difference between ideal and practical operational amplifier. There are various parameters by which we can differentiate between ideal and practical operational amplifier. The parameters are bandwidth, second one is a slew rate, third one is a open loop gain, next one is called as common mode rejection ratio, fifth one is called as a power supply rejection ratio, next one is the input impedance, output impedance and offset. According to your syllabus, you need to know some of the parameters. First one is the bandwidth. Bandwidth is the range over which my amplifier works, that is called as bandwidth. Ideal operational amplifier, this parameter is infinite, means infinity. That means infinite. Infinite means ideal. According to the ideal operational amplifier, the amplifier will work for any frequency range. But practically, if you take particular operational amplifier with 741, which works over 1 megahertz frequency, that is called as a bandwidth. Second one is a slew rate. Slew rate is the so before moving to the slew rate, let me explain you. Bandwidth normally explained, normally expressed in terms of and decibels. In terms of decibels, here you can see in terms of gain and decibels. So it is the range over which the particular amplifier works. In the diagram you can see y-axis shows the gain, open loop gain, and x-axis shows the frequency, and as the frequency increases the gain decreases. So slew rate represents the fastest response that the operational amplifier can have. For example, when you give the input, how quickly the output changes with respect to the time, that is called as a slew rate. So slew rate is represented by lambda V out by lambda Vt. So open loop gain, third parameters are the open loop gain. When no feedback is given or when no feedback path is used, the voltage gain is maximum, and that is called as a open loop voltage gain and designated as a AOL. Fourth one is a common mode rejection ratio. The ratio of a differential gain to the common mode gain in amplifier is called as a common mode rejection ratio. So common mode rejection ratio indicates the ability of the amplifier, how it will reject the common mode signal. Normally, so we know AD is the differential open loop gain, and AD is nothing but that is output divided by input. Similarly, we have one more parameter that is called as a common mode gain. Common mode gain is represented by AC. Suppose VI and VI and VNI are the two voltages we are going to give to the terminal of the operational amplifier. Then common mode gain is represented by actually VI plus VNI divided by 2. So common mode rejection ratio is represented by AD by AC. AD by AC, this parameter tells to what extent the amplifier will reject the common mode signal. To what extent the amplifier will reject the common mode signal. That is called as a common mode rejection ratio. So let me do a small correction, that is AC is equal to, let me write here, AC is equal to, that is common mode gain is AC is equal to V0 divided by V inverting plus V non-inverting divided by 2. So finally, by getting differential gain and common mode gain, you can derive the equation, that is common mode rejection ratio. This is the best parameter to determine to what extent operational amplifier will reject the common mode signal. Actually, according to the definition, operational amplifier is a high gain, high bandwidth differential amplifier. It should amplify the different signal, not common mode signal. So this parameter is mainly used for this analysis. So next parameter is the input impedance. It is the impedance looking into the input terminal of the operational amplifier. Then one is the output impedance. It is the impedance looking into the output terminal of the operational amplifier and ground. So next one is the settling time. It is the settling time is the time taken by the operational amplifier to settle to achieve the specified accuracy at the output. Suppose when you are giving an input, the output changes and output will take a time to settle to the final value, and the time to settle to the final value in the tolerance band is called as settling time. So now here these are the parameters we have discussed right now. Bandwidth in ideal operational amplifier it is infinite or infinity, and but practical value is 1 megahertz. Slew rate is ideal operational amplifier, it is infinite and practically 0.5 volt for microsecond. Normally slew rate is expressed in terms of microsecond. Open loop gain it says like for ideal operational amplifier it is infinite, for practically it is 200,000. Then common mode rejection ratio, once again it is infinite and but practically it is 90 dB. Then we have input impedance, it is infinite and practically there is a input impedance around 2 mega ohm. Output impedance it is 0, practically there is a output impedance of 75 ohm. So these are the parameters we have discussed now. Now let us move to the operational amplifier IC. This is the 741 operational amplifier IC. This is the 8-pin IC. Here you can see the pin number 1 is something like offset. Pin number 2 is inverting. Here we are giving the inverting voltage, and pin number 3 is non-inverting, and pin number 4 and 7 are plus VCC and minus VEE, and pin number 6 is the output. So students, here you can see the representation of operational amplifier. Once again let me repeat, this terminal which is represented by minus is called as inverting terminal. The plus the symbol is used to represent non-inverting terminal. Other than that we have biasing voltage plus VCC and minus VE and output. This is the IC diagram. And one more thing you have to remember here, when you connect the operational amplifier in this fashion, that is when you give the input to the non-inverting terminal, inverting terminal, the output is you can see here, output is out of phase with the input. That is when you give the signal, input signal like this, you will get the output signal out of phase with the input. Now when you connect the voltage source to the non-inverting terminal, here in this diagram you can see when you connect the voltage source to the non-inverting terminal, that is the positive terminal, the output is in phase with the input. So output, here you can see input, and here you can see output in phase with the input. So here you can see the output is out of phase, like 180-degree phase shift with the input. So this is the connection of operational amplifier with respect to inverting and non-inverting. So in the next session we will see the how operational amplifier can be used as a multi-vibrator. Hello student, welcome to the one more session of analog and digital electronics. In the last session we have discussed various components or various parameters of operational amplifier circuit. We have discussed what is operational amplifier and what are the very different parameters of operational amplifier circuit. In this session we will see the application of the operational amplifier, by using multi-vibrator circuits. So multi-vibrator is like an oscillator, is a circuit with a regenerative feedback which produced first type of waveform. There are three types of multivibrators are there. One is called a stable multivibrator. Second one is called a monostable multivibrator. Third one is a bistable multivibrator. That astable multivibrator has no stable state. It will switch over from one state to other state. That is, it switches between two states continuously. So this action produces a square wave pulse at fixed frequency. Monostable has one stable state, but it can go to the other unstable state and it will return from that state to the stable state. Bistable has a circuit as a both states are either in stable state. So now a stable circuit, suppose a stable circuit it switches from one state to other state, like 0 to 1 and 1 to 0. You will get a square wave type of waveform at a fixed frequency. This is the astable output of a stable multivibrator. But it's same thing in case of monostable is it will remain in the stable state. It will remain in stable state. When you give trigger pulse, it will move to the unstable state, and it will remain in that unstable state for some time. After that, it will return to the stable state. Once again, when you give the trigger pulse waveform, pulse, it will return to the unstable state. So if you take here, this is the stable state, then it will go to unstable state, then it will return to stable state. When you give the trigger pulse, it will go to the unstable. This is also called as a one shoot multivibrator. That means when you give the trigger pulse, it will move to the other state, unstable state. Suppose in the other way, you can take like logical 1 is a stable state. So initially it is in logical 1. Initially it is in logical 1. When you give the trigger pulse, it will return to unstable state, and once again when you give the, and it will remain in that state and it will return to the stable state. Similarly, when you give the trigger pulse, it will move to the unstable state. So here this is the stable state, and when you give the trigger pulse, it will move to the unstable state. Then it will return to the stable state, so on. So this is the difference between a stable and astable and monostable. So monostable has got one stable state, and it will transient from one stable state to unstable state. But astable continuously it will switch over between a stable. It will switch over between two states. There is no stable state. So this is the difference between monostable and astable. So students, so we are using timer IC, 555 timer IC. First we'll see the diagram of a 555 timer IC. Here you can see this is the diagram of 555 timer IC. So this is normally used in to implement the multivibrator by using multivibrator and astable and monostable multivibrator. So here in 555 timer IC, it contains mainly 3 resistors which is connected in series. So here we are using 3 resistors of 5K. That's why the name 555. Other than that, we have 2 comparators, and we have one RS flip-flop and discharge transistors. So this is the internal block diagram of 555 IC. So other than that, we have here pin number 8 is connected to VCC, and pin number this one is connected to ground. We have pin number 2 is called a trigger, 7 is called a discharge, and 6 one is called a threshold, and 5 is the control, and 3 is the output, and 4 is the reset. Let me explain you this one by this diagram. Here this is the IC pin diagram of a 555. This is the 8 pin IC. So pin number 1 is ground, 2 is the trigger, 3 is output, 4 is a reset, 5 is control voltage, 6 is threshold, 7 is a discharge, and 8 is a VCC. So this is the 8 pin IC 555 timer, and these are the various pin configurations of 555 timer IC. So now how this 555 timer IC works. So in order to understand the working of 555 timer IC in the monostable multivibrator, let us use this circuit. So this circuit contains once again 555 IC timer IC. Along with that we have connected two external resistors, that is two passive component. One is a resistor and other one is a capacitor, RA and RC. RA is connected between pin number 8 and pin number 7 of the IC, and capacitor is connected between pin number 6 and ground. Other than that, here we are giving trigger pulse at pin number 2. So trigger pulse is a negative pulse. It is a negative pulse, negative going pulse. So initially the voltage of the trigger pulse is 5 volt. So 5 volt. So now let's see how this works. Before that, we have to understand the working the truth table of SR flip-flop. The truth table of SR flip-flop. So we know what is a flip-flop. Flip-flop is a memory element which can store either 1 or 0, binary 1 or 0. So there are different class of flip-flops are there. One is SR or RS, second one is D, third one is JK, and fourth one is T. Now what is the truth table of SR? Let me take you to the board, and the truth table of SR. So here SR or RS. So we have, when you take RS and Y is the output, or Qn plus 1 is the output of the truth table. So when you take the value of R and S is 0, 0, output is in last state or no change. When you take the value of R is 0 and S is 1, it is going to be said as a set, or output is 1, or flip-flop is going to be set as set and output is 1. When R is 1 and S is 0, then flip-flop is going to be set as a reset and output is a 0. And when both are 1, then that condition is called as illegal condition or forbidden. That means this condition is not possible, forbidden condition. So this is the output of the RS or SR latch or truth table. So now moving on to the circuit diagram. So this contains, as I explained earlier, this contains three resistors. So timer, basically timer IC. The timer IC contains three resistors, that is 555. So three resistors of 5 kilo ohm are connected in series in voltage divider basis. So now we are taking here two node point. So one node point is this one, other node point is this one. Now we have to measure the voltage at this point. To measure the voltage at this point, so we need to apply voltage divider resistor network law. According to the voltage divider resistor network, so what is the voltage at this point? Voltage at this point is sum of the resistor from here to the ground, that is 10K. Let me write here 10K, and total resistor, that is total resistor is nothing but 15K into VCC. So this is nothing but 2 by 3 VCC. So voltage at this point is 2 by 3 VCC. Similarly, voltage at this point is the sum of the resistors from here to the ground, that is 5K, and total resistor is 15K into VCC, that is nothing but 1 by 3 VCC. So we are taking two control nodes. One is 2 by 3 VCC, second one is 1 by 3 VCC, and we have connected this to the two comparator. First one is called as a upper comparator, second one is called as a lower comparator. lower comparator. Other than that, as I said, we have connected two resistors, we have connected two passive component. One is resistor RA, second one is C. We have connected something like this. So now we will see the working condition of this one. Initially we will take the value of the, initially we assume the value of Q. We will assume the value of flip-flop output Q is 1, that is Q bar is 0. Here our output is nothing but Q bar is 0. So we will assume the value of Q is 1. When Q is 1, this signal is connected to the base of this transistor, and this makes this transistor to conduct something like this. So there is a path established from here through transistor to the ground. That means now the capacitor is not getting charged. So the voltage at this point is somewhat 0. So the voltage at this point is 0, and voltage at this point is 0, and voltage here is 2 by 3 VCC. That means negative is greater than positive, the output is 0. You will get 0 output. Similarly here, as I said, trigger input is a negative going pulse. Initially the value of trigger input is 5 volt. So this is 5 volt, and this is 1 by 3 VCC. So once again here also negative is greater than positive, so you will get output is equal to 0. When both outputs are 0, according to the flip-flops, SR flip-flop truth table, you can see according to SR, when both R and S is 0, it will maintain the last state. So what is the last state here? Last state is 1 and 0. That means it will maintain the output 1 and 0 as it is. That is, output is 0 and this is 1. Now when you apply the negative trigger pulse, this value, the voltage at this point, pin number 2, the voltage at pin number 2 becomes less than 1 by 3 VCC. Here you can see in this diagram. Let me zoom it. Here you can see when you apply the trigger pulse, the voltage goes below 1 by 3 VCC. So yeah, when it goes below 1 by 3 VCC, that time positive becomes greater than negative. When positive becomes greater than negative, the output of the comparator, let me change the color here. So the output of the comparator becomes 1. And here output is anyway 0. So this time reset is 1. Reset is 1 means, according to the truth table, when reset is 1, you just see, I will take you to that this one. When reset is 1 means output is 0. So when reset is 1 means output is 0. So here you will get output is 0. Here you will get output is equal to 0, and this then Q becomes 0 and output becomes, our output is Q bar. Please remember, our output is Q bar. Q bar becomes 1. Our output becomes 1 and Q becomes 0. When Q becomes 0, this will cut off this transistor. When this will cut off this transistor, that means this transistor will not work, and this in turn recharge the capacitor through RA. Now our capacitor will go into recharge. So our capacitor will be going to recharge through RA. So when the capacitor recharges, that time when the capacitor recharges. So initially let me draw here. Initially uh, the output is 0. Then when you give the trigger pulse, output goes high, and the capacitor recharges. When the capacitor charge reaches 1 or 2 by 3 of VCC, when the capacitor charges reaches 2 by 3 VCC, that means when the capacitor charges above 2 by 3 VCC, now that time threshold voltage 2 by 3, above 2 by 3 VCC, the output of this comparator becomes 1. And here anyway trigger pulse is 5 volt. When the trigger pulse return to this original value, that is 5 volt, this value is 0. That means 1 and 0. When S is 1 and R is 0, flip-flop is going to set. That means it becomes 1 and output becomes 0. So now it becomes 1 and output becomes 0. When it becomes 1, this will in turn switch on this transistor. Now capacitor, there is no way this will in turn switch on this transistor, and the path is established something like this. Now the capacitor discharge. So capacitor discharge. So suddenly you can see the value of the capacitor, value across the capacitor will discharge. So this will continue, this waveform will continue. Let me show you the waveform here. Let me erase this one and show you the waveform here. You can see here. So as I explained earlier, so these are the two passive components. R and C we are going to connect, and here we are giving the trigger pulse. So initially the output voltage across the capacitor is 0, and output voltage is 0 volt. When you give the trigger pulse, output goes high and capacitor will get recharged. When capacitor charges reaches to somewhat above 2 by 3 VCC, then output goes 0. That because output of the upper comparator will become high, and output goes 0, and capacitor will discharge immediately. Here you can see. So this will continue. That means when you see, this is the stable state. So when you give the trigger pulse, it will move to the unstable state. It will remain in the unstable state as long as the capacitor gets charged to 2 by 3 VCC. When the capacitor charges exceeds 2 by 3 VCC, then it will come back to the original state. And once again, whenever you give the trigger pulse, it will once again move back to the unstable state. So this is the working condition of a monostable multivibrator. Now we need to derive the expression for the monostable multivibrator. Let's move to the let's see how to derive the expression for the monostable multivibrator. Here you can see. So T1 is the time taken by the capacitor. To charge from 0 to 2 by 3 VCC. So voltage across the capacitor increases exponentially, and it is given by Vc is equal to VCC into 1 minus e raised to power t by Rc, where Rc is the time constant. Since the capacitor charges through Ra, we will replace R by Ra. At t is equal to T2, here you can see at t is equal to T2, the value of the voltage across the capacitor is 2 by 3 VCC. So at t is equal to T2, the voltage across the capacitor is 2 by 3 VCC. That means Vc is equal to 2 by 3 VCC. So 2 by 3 VCC is equal to VCC and VCC into 1 minus E T1 by RAC. So now you know this and this will get cancelled, and when you solve this one, you will get the equation T1 is equal to 1.1 into Ra into C. T1 is nothing but the time taken by the capacitor to charge the time taken by the capacitor to charge from 0 to 2 by 3 VCC. So T1 is equal to 1.1 by 1.1 into Ra into C. So this expression is very important. So now we'll see some of the problems related to multivibrator. So main application of the multivibrator is it can be used as a frequency divider and a missing pulse detector, pulse width modulator. So the first example, we'll see the first example, we'll see the first problem. For a monostable multivibrator, that is time delay is given 100 millisecond and resistance is given, calculate the capacitor value. That means we know the equation, that is T1 is equal to, we know this equation, this is the equation, right? We know T1 is equal to 1.1 into RC. We know R, we know T1 is 100 millisecond and we know R. So if you substitute this one, you will get the value of the capacitor. Capacitor value is nothing but 0.865 microfarad. So this is the first problem. Second problem we'll see, design a monostable multivibrator using 555 timer to produce the output pulse width of 20 seconds. So you need to design a monostable multivibrator using circuit, monostable multivibrator circuit using 555 timer to produce the output pulse of 20 second width. So now here T is given, that is 20 second, and we have you have expression T1, we have expression T1 is equal to 1.1 RC. Here R is not given, C is not given. Since that's why we need to assume the value of C. Let's assume the value of C is equal to 150 microfarad. So when you assume the value of C is equal to 150 microfarad, and since T is equal to 20 and 1.1, substitute the value, you will get R is equal to 121 kilo ohm. You will get the R is equal to, value of R is equal to 121 kilo ohm. So we'll see, we'll move to the next problem. Find the resistive element value to generate T is equal to 10 millisecond using 555 timer as a monostable multivibrator. Assume C is equal to 0.47 microfarad. Here the value of C is given and we know T1 is equal to 1.1 RC. We don't know R, we know T1. T1 is equal to 10 millisecond, 10 into 10 to the power minus 3. We know 1.1 and we don't know R, we know C is equal to 0.47 microfarad, that is 0.47 into 10 to the power minus 6. When you solve this one, you will get R is equal to 19.34 kilo ohm, 19.34 kilo ohm. So we will move to the next problem now, student. The next problem is design a timer that can turn on heater immediately after pressing the button, and it should hold the heater on for 10 seconds. So you need to design a timer that can turn on the heater when you switch on the button. It should hold the heater on for 10 seconds. So T1 is given here. T1 is 10 seconds. So T1 is 10 seconds. So you need to select the capacitor value 47 microfarad and T1 is equal to 1.1 RC. T1 is given. R is, we don't know the value of R. We know the value of C. So substituting the value, you will get 193.42 kilo ohms. So resistor, this one is 193.42 kilo ohms. So this will generate the approximate timing circuits. So with this, students, we have completed monostable multivibrator. In the next class we will see astable multivibrator and related problems. Thank you.